Hey, Nathan, are you there? I think there should be, this is like a question and answer thing. I think there should be a chat. Okay, I see a couple people now. I think there should be a group chat. If you look to your left, there might be a little toolbar, or if you might have to hover or something. At the very top, there's like a blue square with some lines in it. That's a chat thing. Okay, so I'm seeing some questions come in. Apparently they have a Q&A thing that's different than the chat thing. So could you try to connect to the chat thing and chat on that? This was interesting. Okay. Hey, Nick. You're not seeing anything. Pablos, I don't know. I'm not sure. I might make it available, might not. Nathan, you're not seeing anything. Okay. Um, hmm. Maybe there's an invite mechanic. Not sure what that means. Oh, mechanism or something like that. Yeah. Jeez. Okay. Or maybe the chat's for presenters or something. Man. For the chat on the top right, there's a 9-button thing and it has Q&A there. Maybe you can make a chat and we can select from there. Yeah, it's weird. I don't know. I'm not seeing. I have the chat, but I'm the only one in it, so I'm not sure how to get other people in it. I'm wondering if the chat is only for presenters or something. Because above the Q&A thing, I see something with tags, which is a showcase thing. I see a green button that's the screen share button, and I see the blue button that's the chat button. Hey, Jed. Yeah, if that's the case, then it's too late because you can't add things after you've started. So I see the chat thing. So I'm wondering if the chat app is only restricted somehow or something. Let me look for 2 more minutes to see how to set this up. Okay, I just did a quick search, and yeah, it looks like chat's only available for people that are presenting. And if you're just viewing, you can't use the chat app. I have no idea why they did that. But it looks like you can ask a question. So let's use the Q&A thing to ask any questions that are related to what's going on. Okay. And I guess we'll just go ahead and get started. It's about 5 minutes after. We'll see. And I've seen some people who have been here at this presentation before. I think I'm going to cover basically the same stuff I've covered before. But if you have questions or whatever, you're free to ask them. And yeah, that's fine. Okay, so let me get started. Let me share my screen. Okay. All right, everybody should be able to see the slides now. This is building single-page applications with ClojureScript and Reagent. All right. And what we're going to do today is I'm going to give you a quick overview of this demo app we're going to build. It's a very simple demo app. But it'll give us an idea and give us a good introduction to how to use ClojureScript and Reagent to build single-page apps. And then I'll introduce the language and the concepts and the tools, and the language will be kind of a review for you if you know Clojure, but it might be a good introduction to Clojure if you are new to it. Okay. Then we'll walk through the actual code of the demo app, and then we'll have some time at the end for questions and stuff. And I don't have the slides or the code available anywhere, but you can email me at julio@eastern.com, and I will send you a copy of them when they're available. And what we're going to build is a simple app that lets you create different activities and then count every time you do them, kind of a quantified self tool. So every time you grab a drink of water, you can increment the drink water count, and every time you stand up and stretch, you can increment that. It's pretty straightforward, but it shows us how to build a simple single-page app. And let me switch over to that app. I have that app running now. And so, for example, every time I take a drink of water, I can increment that, and we'll notice that the count to the left here increments for drink water, and the total sum increments at the top there for the things I've done today. This, of course, is a very basic kind of layout, but it should get us started. And I'm sure many of you are much better designers than I am and can make this be much more attractive and much more useful. This particular app doesn't have any kind of backend or anything like that. It doesn't store any of the data anywhere. So if you just refresh the page, everything goes away. But then you can add back the things, or you can add back the activities that you want to track, like take my vitamins. I do that add, and every time I do that, every time I take a vitamin, I can click on it, click the button, and drink some water. I can click it, and it all works like that. So that's the basic app. Any questions about that? Yeah, feel free to use the Q&A area if you have any questions about things, okay? Okay, so about me, I really like building distributed apps, particularly ones that are data intensive, that operate in near real time, so you get that feedback right away with rich reactive front ends. To do that, I really like Clojure and ClojureScript. I'm a huge fan. I'm also interested in Elixir, Phoenix, and Elm. You'll see that some of the ideas for Reagent, I think, have been borrowed from Elm, and that's really awesome. And I'm interested in embedded programming, and that's probably what I'm most interested in Elixir about. There's a project called Nerves that lets you build Elixir apps for embedded computers, which is kind of cool. I've been a developer for a long time. Did a lot of Java back in the day, and then Objective-C for many years. And then the last few years been Clojure and ClojureScript. And I'm a consultant, so if you need a ClojureScript developer or a mentor or a trainer, I'm available for that hire. And Julio Barros on Twitter, which might be the easiest way to get a hold of me. You can comment or ask questions about the talk or ask me anything you want on Twitter. That'd be awesome. Okay, so we're going to start with ClojureScript. ClojureScript is a Lisp that targets JavaScript. Clojure is a Lisp that targets JVM, but ClojureScript compiles down to JavaScript. Clojure and ClojureScript are very similar. They're pretty much the same language. A couple differences that are imposed by the underlying systems. JavaScript is different than Java and so on, but they're very similar. It's a very simple language. The data is immutable by default, which is a little bit unusual, but you'll see, it's a little bit unusual for the popular languages out there, but you'll see many languages are moving towards that direction or add libraries or extensions that let you have immutable data. And it takes a functional approach, which not an object-oriented approach. So a lot of people coming from an object-oriented background, might need to learn some new functional ways of doing things. It uses the similarly named but very different tool called Google Clojure Compiler for optimization. So it can create a minimized JavaScript file that's a lot smaller than many other systems. Now, the Hello World version of that is a little bit bigger than you think it should be, but the good thing is it doesn't get much bigger than that. As you add more and more code, the actual minimized file does not grow out of control. It interops well with JavaScript, so you can you can call out to other JavaScript libraries, and you can do a lot of types of things that you would normally do in JavaScript. You can do it in ClojureScript. It runs in the browser and in the Node.js, and there's a project called CLJSRN, which uses React Native for native mobile apps. So you can use it to create native mobile apps also. And there's a project called Plank, which is node-based ClojureScript REPL for scripting on the Mac. So it very quickly spins up and interprets ClojureScript. So you can do ClojureScript programming really quickly. Now, when people look at ClojureScript, the first thing they notice is the parentheses, so we want to address that right away. The parens are similar to the types of parens you'd use in other languages, except the number of parens is pretty similar, except that they usually go around. They always go around the outside of your whole statement. In a lot of languages, you might have an object dot a function, an open paren, and then parameters and a closed paren, and then sometimes a semicolon or not. In Clojure, you'll see the same type of thing where you have an open paren, the function, maybe a data structure that you're working with, and then any additional parameters that you're working with. It's just kind of it's a different thing, but once you get used to it, it's very, it seems normal and it seems fine. The other big thing that some people ask about is that it's not statically typed or strongly typed. It's a dynamically typed language. So if you're used to things like Java or other languages that are a little bit more strongly typed, it seems odd to put everything in a map, or that functions don't have a return type, or the parameter types aren't there. And that gives you a lot of flexibility, but if you're not careful, it can be a bit of a hassle. Because you end up passing things to functions that are not the types that the function expects. Luckily, there are a couple of tools to help, and that's just the way Lisp and Clojure work in general. So that's a trade-off you make. Luckily, there are a couple of tools to help you with that trade-off. There was just recently announced a new core library, or a core, I guess it's a library, or feature of the language that is in alpha right now, but it should be coming out soon, called Spec, that helps you define constraints and contracts, kind of checks for your functions and the types that you expect, and also will help you create generative testing so that it will automatically create tests for you. So if you say your function returns an int or something, or takes an int, it could generate a bunch of tests with a bunch of different ints, including negative integers, 0, positive integers, big integers, little integers, and so on. That way you can test your function under many different conditions. And there's also an older system, a more established system called Climatic Schema that a lot of people use and like. And then there are also many, many validation libraries out there that you could use. So let's talk about some of the basic data types. And the core data type here is a list. A list is essentially a linked list, if you know what that is. And it's denoted by the round parentheses, or the round braces. List is just a sequence of things. And the special thing about lists is that the first thing in the list, when the system gets it, it tries to execute it. So the first thing in the list is usually a function. If for some reason you don't want the function to be executed, or you don't want this list to be executed, you have to quote it, or you have to tell the system not to execute it using their quote form, basically. So as it says, it's open paren function and then any parameters and close paren. So if you got to add two numbers, you do open paren plus, and then the first number and the second number, and plus is an actual function, not just an operator in the language, but it's a function that gets called. If you don't do that, if you have open paren 1, 2, 3, it'll try to execute 1 as a function, and you'll get this error that says 1 is not an IFN. IFN stands for function interface, and so what it's telling you is that it can't execute 1, so it doesn't know what to do. So to avoid that, if you want a list with the numbers 1, 2, 3, you quote it, you put a little tick mark before it, or you can use the quote form, but a tick mark is fine. And most lists use list almost exclusively or everywhere, but Clojure also introduces vectors, and vectors are essentially one-dimensional arrays, and they're denoted by the square brackets. They're very similar to lists, except that they're not linked lists, and the underlying implementation is different. But the big thing is the similarity is that they're both sequences of things, and then the big difference is that the system does not try to run vectors. It says, oh, that's just data, I understand, no problem. So you can just say square bracket 1, 2, 3, square bracket, and that's in many ways very similar to the list 1, 2, 3. Then you can pass the vector as a parameter to something, to a function like count. You can say open paren count, square bracket 555, square bracket close paren, and that saying is run the function count with a parameter that's the vector 555. That vector has 3 elements in it, so the answer comes back as 3. Another common function is get, which takes something out of a data structure, and vectors are 0-based. So if you say get from some vector, or the vector 1, 2, 3, get the thing in the first position, you'll get back the value 2 because it's 0-based. So 1 is 0, 2 is in the position 1, and 3 is in the position 2. And you can have, vectors can have mixed types. So you can have all kinds of things in vectors, including numbers and maps and other vectors and other lists and lists of vectors and stuff like that. So you can have any kind of types inside of a vector, or any kind of type inside of any of the other data types. Maps are key value pairs. They are called hash maps or dicts or hashes in other languages. Here they're called maps, and they associate keys and values. They're denoted by the curly braces. And an interesting thing is that anything can be a key and anything can be a value. So you can put functions in values, you can put strings as keys, you can put numbers as keys, you can put other data structures as keys, including other functions as keys. I don't know why you'd put another function as key, but you can do that. And it's kind of common, or there probably is a good reason to put another data structure as a key. But the easiest way is to put either strings as keys or numbers as keys, or keywords as keys. Keywords, as we'll see here, first name, it's almost like a string, except it's a special string. They evaluate them to themselves. They start with the word colon. Other languages have keywords, or they call them symbols, maybe in other languages where the colon's at the end. This is a very similar concept. And then getting values from a map, you can, if I define a map, M, that has the keyword, the key colon Y, which is a keyword, and then the string because, that's my key value pair. And from M, I can get the value for the keyword, or for the key colon y, and it returns because. Also, for shorthands, the keywords are also functions, so they can be in the first position of the map, the first position of the list here. And so the keyword y knows how to look itself up in the map m. And then you can also switch it around too, where the map is also a function, where the map m knows how to look up the keyword y, the key colon y. So you'll see all three of those formats for getting values out of maps. And I don't have a chat, so I just want to make sure that if you have any questions or anything, just go ahead and ask the questions, and I will try to address them as we go. Okay. Adding stuff to a data structure. Often you want to use the function assoc, and assoc adds a key to a value in a map. The key thing here is that we said the data structures are immutable, so it doesn't actually add it to the old map. It actually creates a new map that has the new associated values. So if I have a map that says colon name is Julio, and I add the key loves and the value closure, I get a brand new map that has the two keys and the two values I just specified. The old map stays exactly the same. It does not get modified. So in this example, I have x is 5. I can associate in y is 3. I get a new map where x is 5 and y is 3, but the old map, map m, is still x is 5. So the basic interesting types are double quotes denote a string. There's no single quote string in Clojure. It's just always a double quote. Colon a word is a keyword. It's kind of like a special string. I think it's hard to explain, but a lot of languages have keywords or symbols or something like that. And then if you don't have strings or colon, then what you have is what Clojure calls a symbol, which is basically the name that you use to refer to something. So you have the name of a variable or the name of a function, and those things are called symbols in Clojure. You have integers and you have doubles, so you need to say, if you say 3.0, you end up getting a double. The curly braces denote a map. Square braces denote vectors. Parentheses denote lists. Again, remember lists, the first thing in a list gets executed, so it should be a function. And then pound curly brace is a set, where a set is just an unordered collection with no duplicates. So if you wanted to get all the unique names in something, you could put them in a set, and then all the duplicates would be removed. And then collections can contain any of the other collections, plus functions, plus anything you want. So putting functions in there is kind of useful because, oops. Okay. I'm sorry, I just got an email from somebody. That's good. Asking for the slides. Okay, so putting functions in maps is pretty useful. You can kind of create a very simple object kind of structure where you have keyed functions that you want to call different types. It's kind of an advanced thing. Excuse me, it's kind of an advanced thing. That's kind of an advanced technique, but well, not too advanced, but it's an intermediate technique that could be very helpful. All right, so we have a question. Jeremy asks, is a symbol the same as an atom? So an atom in Clojure is something different than a symbol, so no. But you would use a symbol to refer to an atom. The symbol is basically the name of the variable. So the symbol could refer to an integer, it could refer to a map, it could refer to an atom. But then the atom is the actual value, the thing that's being referred to. So no, not exactly. I hope that's clear. We'll talk about what atoms are in a little bit. Okay, functions. Functions take 0 or more input parameters and return a single value. But the return value could be one of the data structures. So it could be a map or a vector, or it could be a list of things. It could be anything you want. And it returns the result of the last expression executed. So your function can have multiple expressions in it, but it's the last one that generates the result value. And you can define a function using the shortcut defn, which is define function, and then the symbol here, my function name, that's the symbol, and that is going to be the name of your function. So that symbol is going to refer to this function. You can have an optional documentation string, and then a vector that's going to list all of the parameters this function takes, and then what you're going, and then a list of functions or a list of expressions that get evaluated there. So you can call function A with parameter 1. You can call another function B with parameter 1 and parameter 2, and then that last expression is what gets returned. What is the return value of this function. So you could define something like increment. There's already an inc function in the system, but you could define increment, which adds 1 to whatever number you pass in. You pass in a number, and it's denoted by the square brackets, and then the expression you're going to evaluate is plus 1, and then a number. And so whatever you pass in will add 1 to that, and then we'll return that value to this. Defn is just a shorthand for def, and then fn is the shorthand for a function. So def 2 times is defining a variable, because I don't have another word, that's the common word, with a name 2 times that's going to refer to a function that otherwise would have been anonymous, that takes this fn function, it takes a parameter x, and then it multiplies x by 2. And triple does the same thing, but it uses an even shorter version of a function definition, where it's a £, open paren, and then the single expression times 3, and then the percent sign just means the first actually it means all parameters, but in this case we're only going to accept one parameter. You can do %1 if you had multiple, and %1, %2 if you had multiple parameters. This also defines a function called triple that takes 1 parameter that then multiplies it by 3. This can be really handy, but it's can be hard to read and hard to explain. It's usually best left to situations where you're going to have very, very simple functions and you want to define something inline that's just something like this, that's times 3. If you have anything a little bit bigger or more complicated, you might want to use the function thing so that it's a little bit clearer what it is. The fn version or the defn is probably the most common, but you'll definitely see the pound open paren syntax for defining a function very quick, very often in when you have short inline functions. Okay, some people have heard the term pure functions. The idea is that pure functions don't modify any state, they don't have any side effects, and they always return the same value for the same input. So inc3 is a pure function. It should always return 4. There's nothing, it's not looking at some state somewhere. It's not an object with instance variables or anything like that. It should always just return 4. Whereas some other functions like rand is impure. There's actually a random number generator somewhere that you can seed, and depending on how it works, it has a state that then gets updated every time you call it, so you always get a different value. In general, I think impure functions are necessary because you need to be able to do something different. You need to be able to have the system save things and do things, but they can be harder to test than pure functions. So in general, when you start writing code, you want to design things to use as many pure functions as possible, because once you test them, they're always going to work. You don't need to do mock things up. You don't need to do a lot of setup. You don't need to do a lot of complicated testing, because you can just test the function directly. Okay, and so a bunch of common functions, which if you've seen other languages, you'll probably have seen versions of these. I know that they're in Ruby and JavaScript and everything. Map. The word map also refers to the data structure, and it returns to this really common function too. I wish there was 2 different words, but it's not the case. So map will take a function and apply that function to every item in a sequence, in a list or in a vector, and it'll return the result. It'll return a sequence of the result of that function being applied to everything in the original sequence. So if you wanted to increment everything in a list of numbers, you can map inc across that list, and then you'd get a new list that was just as long as the original list, that had members that were the values that were incremented from the original list. So, so that's a really common approach. Reduce is a thing called fold L in other languages and functional languages, and the idea here is you apply a function to everything in a sequence, but you also have this accumulator value. And so what you're trying to do is get one value out of it. So if you needed to do like, well, there are easier ways to do an addition, but the kind of example, the classic example is if you wanted to add everything in a list, you could reduce across that list, and then you can look at every number in turn, and then you have an accumulator that you can start adding numbers into. So then you return the accumulator at the end, and then that can be the sum of all these numbers, or whatever it is you're trying to do with all these numbers. There are easier ways to apply to add a sequence of numbers, including apply, which is the next one, which is to call the function with the items in the sequence as a parameter. So you can say apply plus open paren 1, 2, 3, and that's the same as calling plus 1, 2, 3. I just realized I should probably have examples for all these, but I'll have to update these slides. Filter and remove go through a sequence and either keep or remove things that match some kind of predicate. So if you had a list of numbers, you could filter, and that filter means keep the even ones by passing in the even question mark as the predicate, or you could remove the even ones by passing in the even question mark as the predicate. Anything that matches the predicate either gets removed or kept depending on which function you're using. Assoc and dissoc are common functions to add and remove things from a collection. So if you have a map, you can assoc in new values. You can dissoc you can use dissoc to remove old values too. Assoc in is pretty similar, but when you have a nested map, you have a nested maps, it can be a little bit easier to use assoc in to navigate in. So if you have well, I'll have examples later. And then update in is the same type of thing, except assoc takes a value that's going to get placed in a nested set of maps, but update in has a function that's going to be applied to the value there at that point, at that path. And again, the paren hash sign open paren close paren is an anonymous function. And we'll start seeing examples of all these pretty soon, okay? So again, something to keep in mind is all the data is immutable. You can rebind the symbols. That means you can have the symbols refer to something different, but it's going to be a different data structure. So I can't say never, but you hardly ever actually change a data structure once you've created it. You just add things, you create new ones by adding things, and you create new ones by removing things, and then you rebind the symbols, the names, right? So in the second example, my defen, X at first refers to the vector that's got two names in it, Joe and Bob. Y then refers to the value that the same vector that X refers to. Then we take X and we rebind it to the old vector plus a new name, Jane. And if you do this, and then if you print X and you print Y, X has the new vector with 3 names in it, whereas Y has the old vector with 2 names in it. So that vector is never changed. I think a lot of systems now are moving to something like this, so using mutable data. I know that JavaScript has map, and ES6 has a bunch of immutable functions that do something like this, but it still also has some functions that are mutable. In Clojure by default, they're immutable. Okay, atoms. Somebody asked about atoms. Atoms are a way to have what appears like mutation, but it's very, very controlled, shared state, synchronous state. And a lot like the other symbols, it doesn't actually change the underlying data structure, but it changes what the atom refers to, and it just does it in a very controlled way, so that you're never in a situation where somebody tries to read the atom while somebody's writing to it, and the system will not get confused. If you ever try to read the atom while in one thread, let's say, while some other thread is trying to write to it, the system will not get confused, and you will get a consistent result out of the system. So it's almost like you're doing it in a transaction or something like that. So so it's just a controlled way of accessing shared synchronous state. So the thing is with atoms is that you have to, when you go to read them, you have to dereference them, and you start off with the @ sign, or the function deref, but a lot of time, most times you just use the @ sign. So if you define A, the symbol A, to be the atom hello world, to be the atom that's the data structure hello world, the string hello world, you can get the value out of A by doing @ sign A, and that gives you hello world. You can change what A refers to using the reset exclamation point, and now A will refer to goodbye. And you can change what A refers to by passing a function to the old value using the keyword and getting a new value out using the function swap exclamation point. So using swap exclamation point for A, we can say make the old value A be the value returned by uppercase, and then the A now refers to the value goodbye. Now this is a string. This atom is a string, but the atom can really be anything, and you'll see that we're going to use an atom that's a map that's going to have nested maps, going to have nested vectors, and maps of vectors of vectors of maps. It's a pretty common thing to do like that. And then that's where you would use swap and update in to pinpoint, to navigate down to a specific place, to a specific entry in this in these nested data structures that you want to update. Are there any questions about that? That must have been confusing. Let me take a break here, and we can talk about anything I've mentioned so far. No? Okay, well, I'll keep going. Okay, so now, when you actually got to use ClojureScript, there's a lot of things you can do. You could use ClojureScript and do direct DOM manipulation, just like you would with jQuery. And there are two libraries out there. You could do it using the Google Clojure library, which has I forget what they're called, but like the get element by ID functions. So you can use those directly, or you could use these other libraries, Domi or Domina, that give you jQuery style selectors, CSS style selectors. Oh, let me pause, because now we do have a question. How often would you use atoms in a real life app? Is this like a variable in other languages? Okay, depends on which kind of apps you mean. In like server apps, if you're writing the web server, you probably would not use very many atoms. You could use some, but you don't treat them like variables. You very rarely create variables that hang around for very long like that. So you can have variables or symbols that are bound to values inside of functions, but as soon as the function ends, those symbols go away. And then you don't use them to like keep track of, if you want to add up a bunch of numbers, it's probably a code smell to create an atom that has the value 0 and then keep updating the atom by adding up new numbers. So that's not the way you do it. In front end programming, though, when you go to do JavaScript, you'll see that we are going to use an atom. We're going to use one big atom kind of as a database for what it is that we're presenting to the user, and then we can use a bunch of smaller atoms for transient state as we're changing things, as we're manipulating the UI. And there, it's more acceptable because I believe because a UI really is all about state, and so you need to maintain that state. Whereas on the back end, it's really more about computation and stuff, so you really don't keep those atoms around very long. So I hope that was useful. Okay. So you could use ClojureScript with Domi or Domina and do direct DOM manipulation. But unless you're going to do something really simple, I don't think this is a great approach necessarily. Just like I don't think that jQuery is a great approach to build big apps. It's fantastic for doing small animations or to do form validations or things like that. But if you've used jQuery before to try to build a bigger app, and you're maintaining the state in the DOM and trying to keep track of everything that's going on there, you'll find that it gets really complicated very quickly. So that's not like the best tool for do that. So Domly and Domina are along those lines. I don't find them that interesting or useful. So I did not use that. I mean, you might like them for something. I don't know, but I didn't find them that useful. But what I did find really fantastic was when a year or so ago, when React.js came out. And React.js has a completely different strategy for creating web applications. It doesn't try to manipulate the DOM itself directly. It has this idea of using JavaScript objects to create a representation of the DOM, a virtual DOM or an alternate DOM, and then it keeps track of what the real DOM is and what this alternate DOM that you're trying to build is, and then it keeps track of what needs to be updated and changed and added and removed and so on. So once that came out and the ClojureScript libraries that wrapped that were available, then that totally changed the way you build front ends. It's a very different approach than something like jQuery. It's a different approach than old Angular. I don't know what new Angular is like, but it's very different than all those things. So if you're familiar with React.js, great. If you're not, there's a lot of documentation out there, so you can see what it's all about. But what you need to know is that there are multiple ClojureScript libraries that wrap or that help you interact with React.js. The granddaddy, a big one is Ohm, and then there's a newer version of that coming out called Ohm.next. That's what a lot of people use. The other really big popular one, I believe, in my opinion, or this isn't as far as I can tell, is Reagent. There's an older one which is what we're going to talk about tonight. It's one I like a lot. It's very straightforward to get started with, and it's really easy to use. It's a good place to start. You might end up liking a different library, and that's fine. But I think Reagent's a great place to start. And I think if you see how Reagent works, if you like something else better, then great. It'll be easy enough to switch over or to kind of compare them. So we're going to start with that. There's another one called Quiescent that people liked a lot. And then there are a couple new ones. I think I've heard a lot of good things about Kichma recently and about Rum and Petrol. If Reagent wasn't available, I'd probably start looking at Kichma more. But I believe any one of these would be a good approach. A good choice or a reasonable choice if you like them better. Ohm.next, I believe, might be the most popular, or definitely has a lot of energy behind it. It has a lot of great ideas. I feel it's a little bit tricky to get started with. So if you're interested in that, then definitely check it out. And if you find it a little confusing or not as intuitive as you'd like, I don't think you're the only one. So just be aware of that. Whereas I think Reagent is pretty straightforward. So like I said, that's what we're going to go with. So we're going to talk about that here now. Okay. So the idea with Reagent is that it's minimalistic, and I find it Clojure-esque because you're just creating functions. And the whole idea is you're going to create a function that's going to return a data structure. And the data structure, which is going to be these vectors of symbols and other functions, gets passed to Reagent. And then Reagent takes that data structure and creates the corresponding React components. And then React takes those React components and does what it does to update the DOM. So these three steps can sound kind of complicated when I explain them, but they're pretty straightforward once you look at how it works, right? So in Reagent, I could have something like, let's start with the footer component right here. It's a function. The function is called footer component. It takes no parameters, and what it returns is this vector that's got the keyword P and a string brought to you by the letter Q. With that, you can kind of see that looks like that's going to be a paragraph that's wrapping the string brought to you by the letter Q. It's not that right now. Right now, it's just a vector with a keyword and a string, but Reagent is going to take that data structure and create the corresponding React components, and then React will take that React components and make sure that they are updated correctly in the DOM and visible in the DOM in the browser. And with Reagent, you can also do something a little bit, the simple component's a little bit more involved than the footer component. Oop, I forgot to fix something here. But the simple component is also a function, and it takes this one takes no parameters, and it's going to return a vector of vectors. And the first vector is going to have the keyword div, and then it's going to have another subvector that's the keyword p and a string. So it's a paragraph component. And then the keyword button, which is going to be a button component, get turned into a button component. And it's going to have a map that has the on-click key and then some function, myClick handler, which is going to be turned into the on-click attributes for the button element in the DOM. And it's going to have the string push me, which is going to be the value of the button. It's also going to have another subvector, which is a keyword p, and then dot some class. In this case, when some class is not a function or anything, it's just a syntactic style that we're saying that we're going to create the p component, a paragraph component, and it's going to have the class some class, and then it's going to have the contents, I have some class. And the last one's kind of interesting, although there's a typo here. The last subvector is a square bracket, so it's a vector. We're not calling it here, but I'm passing in the function footer function. The typo is that really this should be footer component, which is this function I've declared up above. I need to fix that slide. But the key thing here is that we're passing in a function here, and we're passing it in the vector. So the function isn't being executed now, but it will be, Reagent will execute it and then figure out what it is generating, and then substitute its return value and put them in here. So we can use this to kind of create these dynamic components that change any way you want based on whatever it is that the functions are generating. Okay, so that's the key to Reagent. If you have any questions about that, definitely let me know. Whoa, so I'm running late, so this talk is a lot longer than I expected it to be, so I'm going to try to speed up a little bit. So tooling, Lineagen or Boot. Somebody had asked about Boot. These are both tools that you can use. Lineagen's the older one, Boot's the newer one. Some people like Boot. I don't know. I think either one's probably perfectly fine. Use whichever one you like. They handle, well, we'll talk about that in a minute. We're going to use a tool called Figwheel, which is going to handle like the automatic compilation and updating for you. And then we're going to see that you can use a template to set up a project to cut down on some of the boilerplate. Lineagen or Boot, they handle dependencies, they handle compilation, they handle running tests, they handle packaging and deployment. So when you're ready, when your project is ready, you can deploy and generate one JavaScript file that then you can import into your page, and that'll be your whole application. So you can use Line or Boot, either one's fine. Figwheel builds your ClojureScript code and hot loads it into the browser as you're coding. It runs its own server to load assets. It watches and compiles your files. It pushes the changes to the browser. It sets up a REPL in your browser, and it can coexist with your other server if you want. So that's fine. And then there are various templates. The Figwheel template is a good one. The Chestnut template built also adds a backend. There's a Luminous Web Framework, which is really just another template that adds even more libraries, all the libraries you might expect to build an application or web application with. And then there are lots of templates for whatever library you're interested in using. So we can get started. Whoops. We're going to create a new project using this line Figwheel thing. And whoops. Let me close that. So normally you would just say line new Figwheel -- reagent. And this will create a project for you. I don't need to run it because I already ran it. Sorry. I made a typo, but you'll see in the slide it's correct. And you go into the project it creates, and there So I'm in the right place. So you'll see there's a project CLJ file, there's a directory, there's a directory with some more source code in there. There's some resources, including an index HTML file that's going to host your app. And then if you start line Figwheel, it'll compile your project and get it ready to be loaded. You could then bring up a browser. This is the old version, but once it finishes compiling, we can reload this thing, and it just gives you this hello world application. If we look at the source code, we'll see that there's some import and stuff at the end, a lot like other languages. There's this command to enable console print, so you can, whenever you do a print line, it'll go to JS console. There's a print line that says this text is printed, so go ahead and inspect it. So you can go to the console here. Oh, I was on errors. So this text is printed from whatever. So we don't really need that, so I can delete that. I'm just going to delete this comment. We'll see that we have this app state, which is an atom, and it's got the text hello world. So, and it only is defined once. So if I, well, let me get back to that. And we'll see that we have this function hello world, which is our component. The component, this hello world component is what gets loaded here when we say reagent render component hello world at this get element by ID in this app div. So if we look at resources, we'll see that it's just a regular HTML file with one div in it that has an ID app. So basically, this component, which can be made up of many, many subcomponents, will get rendered at the position where this div is with the ID app, because that's what we're looking for, right? And then that component, the hello world component, is this thing here, which is vector, which is this h1 and then some text. And the text here in this example comes out of the app state, which is an atom that is a map that has the key text and then the value hello world. If I just change this to give it literal text, like this is literally literal. As soon as I save that, it gets recompiled, and you'll see it gets updated here. Right? It gets changed, it gets updated there right away, very quickly. If I change the atom, it gets recompiled, but it doesn't get displayed right away because of this def once. So this is how we can establish and create a bunch of state in our app, and then debug and keep working on our app without having to reload all the time, without having to get to a particular place, by keeping all the state in the atom. And we'll talk about this a little bit more in a minute. But if I actually reload the page, if I go back here and hit Command R, then it reloads everything, the atom gets redefined, everything gets redefined, and then we get the new values that we're working with. So some things can get updated very quickly, and then some things don't get updated unless you specifically reload the app. And that comes in really, really handy. Another thing to note is that we've created this REPL here, which is this read eval print loop. So in here, we can examine different things. So one thing you can do is you can call functions in the browser. So I can have the browser add two numbers together, and that tells me that. I can have the browser, I can call some JavaScript functions in the browser And if I come over here, you'll see that I've got an alert that's the hey. And I can then examine different the state of my application by switching to this namespace. So I can do print line at app state. It's the name of this atom. And by doing a print line app state, I can see that it's a map where the key is text and the value is this is new. I could change that app state manually here for whatever reason. If I want to do it this way instead of writing code to do it, I can say reset app state to be text. This was set manually. And then that gets reflected in my app right away. So this workflow here, I think, is fantastic, and it's really, really amazing. I know that like React has live reload now, and some of the other systems are trying to do this. But I think that this works really, really well and makes front-end development very, very fast compared to other systems. All right, but let's do some more stuff. So here, let's say hello world. Let's say we want to add a button because we want to change that text not manually, but through programmatically through some kind of UI. So I'm going to actually, hello world can only return one thing, but it can be a vector of things. So I'm going to return a div that's got my h1, but it also has a button. It's going to say push me. And now I see I have the button there. And let's say the button is going to have an action. Let's say on click. And the function is going to be print line hey. Now when I come back here, without reloading anything, I can just push, and you'll see the message comes down, shows up in the console. Now if I want to make that visible, what I need to do is say something like reset app state to text I was pushed. As soon as I do that and it compiles, as soon as I click the button, I can see that I was pushed is updated. And that's the basic functionality for an app, and then we can get a little bit go a little bit longer with this and get more into the details. But I am running out of time, so I am willing to go longer, but I will make sure I give people time to ask questions now, because that is like the key information that I wanted to show. And anything past that, I think, is just more details on how to how to build better, bigger and better apps. So let me take a moment here, a breather here, and ask if there are any questions. Okay. All right. So let's go through the code for getting to the point where we have the bigger app, and we can see how we run that, how we create that. Okay, so one thing you might want to add is to add like Bootstrap or add some CSS to be able to create things to make these a little bit more attractive. So in your index.html, you can add the Bootstrap thing. Why is there an @ for app state? There is an @ because the app state is an atom. And to access an atom, you have to dereference it, and you dereference it using the function deref or the syntactic shorthand @. So when you want to get the value out of an atom, you preface it with the @. Remember, atoms are kind of special things that let you have controlled access to some kind of shared state. Okay. So this is just going back to what we just showed you. This was the core JS that was there before. We can add a button by adding a subvector to the component, and that creates a new reagent component. That's a button. You can make it do something by adding this onClick function. And you can make it visible by having that onClick function do a swap and updating the app state. So yeah, so that's fine. So the example I used was I did a reset. So I just like totally, replace the old value, the old data structure that was in the atom, but the swap will call a function on a particular thing. So the function we're going to call is assoc, and what that's going to do is going to only change the text field, which is the only field in this case, in the atom in this case, and then it's going to change it by whatever this value is, which is the current date and time. So you reset atoms with the reset function, and you can reset parts of it by using swap and passing it the function that you're going to use to update the parts of it. So this is a big jump now, but not really if you start thinking about it. So the quantified self-tracker, if you remember what that looks like, let me actually switch the code, switch the, oops. You switch from here to version of the project. Now this version, we have an H1 that's the me. We have an input field eventually. We're going to have this add button. But the key thing is that we've got these different things we're tracking. It's got a count, it's got a name, and it's got a button that's going to increment this particular thing. So that's what we're going to work on now. And then eventually we're going to be able to do something like push-ups and add that, and then have that be able to increment that. So the code for that is, first we're going to think about, whoops, what our data structure is going to look like, what our little database is going to look like. And we're going to use this app state. That's an atom, and it's going to be a map, and it's going to have counters. And counters is another map where it's going to hold our counters, where they're going to be keyed by the ID, and then the value is going to be a map that has all the different fields in our counter, including the name and ID. I'm just making up the ID so I can tell one counter from the other really easily, and then a field called count that has the current count there, right? So you can see how we could add new counters by adding them to this map, keyed by the ID. We can remove counters by removing them from this map, and we can increment a particular counter by going through counters, ID, count, and then incrementing that value. So that's how we if we can manipulate this data structure, we'll let Reagent and React take care of the rest in drawing it. Then let's start at the bottom. A lot of times it's a kind of a handy way to look at Lisp code. And we have the function hello world. It's a div. It's got an h1. It's got a subvector. It's an h1. It's got the me h1 in it. And then it's got this function here that's going to call for every C in the values in the counters key in the app state. I'm going to create a counter view, square bracket counter view, and pass in the counter I'm looking at. This key IDC is a React thing that's going away, hopefully. Soon it's a way for React to keep track of which div this is when you're creating a bunch of divs that are siblings. This counter view is this function here. It takes a counter, and what it does is it creates a div that's a row. It creates, with the subvector, it's a div, it's a column, and it's got the current count. A div that's a bigger column that has the name of the current counter, and then a div that's a small column that has a button that's got the classes to make Bootstrap draw this well, and it's got a function called onClick attribute. These are the onClick attribute is this function that's going to increment the counter, giving it, and then it's going to call it the increment counter function, passing in the current counter, and then the string done it, and then increment counter is just going to swap into the app state using the function update in at the path counters ID count, and it's just going to execute the function inc. So it's going to follow all the way, look at this global database that we have, and it's going to follow all the way down that path that we give it, and then execute the function at that particular count. So once this data structure gets updated, all the components that rely on this data structure will get updated, and then Reagent, React will redraw the screen, or only the parts of the screens that need to be updated. All right, I think I've gone pretty long on this, but I am happy to send you slides on it. Send you these slides, and maybe I should just answer questions now. This is the code for adding a counter, and all we need to do is add a new entry in that map. You don't need to manage, there's another library called Reagent Forms that can help you create forms really easily, really quickly. There's a library called Q that will let you create the templates in actual HTML, so you don't have to do the square bracket :div stuff. You can actually write HTML if you want. There is another approach that, like the next more advanced approach, is to build this Flux Elm architecture system, which will let you create subscriptions and actions so that you never manipulate the app state directly. You do it only through these actions. And if you're interested in that, if you're interested, it's similar to Flux and Redux, I think. Definitely check out this reframe README. It explains this really, really well. It's kind of long, but it has a lot of great information in it. And basically, you do it through dispatching events and subscribing to changes. And so you can create the different subscriptions that you want, and then you can create the handlers that handle different events as you dispatch them. And then ClojureScript has a lot more really great libraries. Core async, which is basically Go loops, so you can do multiple things at once. It's almost like having threads in JavaScript, which you don't have, but it's really a powerful way to do concurrent programming. There's Ajax and HTTP libraries, and there are libraries for WebSockets and everything else. Plus, you can use JavaScript libraries pretty easily. It kind of depends on the library, but the interop is pretty good. There are tons of resources out there. So as you get the slides, all these are links to different places you can learn about JavaScript, Clojure, and ClojureScript. And then there are a lot of great IDEs. I'm using Emacs, but there are easier libraries to use, including Lighttable and Cursive and Spacemacs if you are a Vim person, and you can use Atom if you're familiar with that editor. And then there's Nightcode and Nightmod, which are also two popular editors for writing Clojure. So now I really am going to stop and just take questions. Okay. Okay. I'm not sure. So Pavel asks, is this going to be on GitHub? I don't know, and but I will send you the code. Just send me an email. I'll send you the code and the slides. I probably am not going to make another video to show this. I think that would be great. I think that's just a lot of information to pack into a video. And I'm experimenting with this format. I think an hour is just not enough time to cover this information. I think this really needs to be more in a class. And I think that writing the web server part of it is also kind of a similar situation where I don't know that I could do a good job explaining that in an hour. But that really needs a class to do that, I think. So I don't know. We'll see. We'll see is my answer. Okay. Any other questions? definitely contact me on GitHub, and I mean on Twitter, and send me emails, and I will send you the slides and the code and stuff. Okay. 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 I don't see any questions. There's still people here on the call, but maybe they've actually fallen asleep or gone to bed or whatever. So I'll just wait a few more minutes till somebody, in case somebody's working on a question, but I think that's about it. Nick commented this chat. I think that's, I have no idea. I wish I understood this all better. Okay, Al. All right, thank you. Thank you. Okay. Okay, thank you, Pavlos. Yeah, thank you. I hope you got a lot out of it. Obviously, I think I need to cut a bunch to have it fit in an hour, and it's just a lot of information. I'm not sure what to cut, but thank you. Okay, I think that's it. So I'm going to stop the broadcast. Thank you. Thanks, Nathan. All right. See you guys on the interwebs. All right. Bye.